Okay guys, let's come to the properties of Hilbert space. Like vector space, Hilbert space consists of a set of function, a set of functions psi, phi, xi and so on, and a set of scalars a, b, c and so on, which satisfy the following properties. The first property is we represent the Hilbert space by H. Okay, the first property is the Hilbert space is a linear space. What it means? It means that the Hilbert space satisfy all the properties listed in the vector space. For example, I will mention a few of them. Here we have a comparison of vector space versus Hilbert space. Okay, in vector space we suppose that we have two vectors psi and phi, then belongs to vector space, then psi plus phi also belongs to the vector space. The same is true for Hilbert space. If we have two functions psi and phi which belongs to the Hilbert space, okay, then their sum psi plus phi also belongs to the Hilbert space. The other property of vector space was, these are the addition rules, okay, that if we have two vectors psi and phi, then they obey the commutativity property such that psi plus phi is equal to phi plus psi. The same is true for Hilbert space. Psi plus phi, two functions psi plus phi, they are equal to phi plus psi. These are the comparison between vector space and Hilbert space. The third property is associative property. In vector space, if we have three vectors psi plus phi plus xi is equal to psi plus phi plus xi. Like if we add the first two vector first and then add the result with the third vector, or if we add the second and third vector first and add with first vector, the result will be the same. The same is true in Hilbert space. If we have three functions psi plus phi plus xi, if we add the first and second function first and then add it with the third function, the result will be the same if we add the second and the third first and then add with the first function. And there are also few other properties of addition rule. Now comes to the multiplication rule. Okay, multiplication rule. schools. In vector space, we say that if psi and phi are two vectors, psi or phi are two vectors, belongs to the vector space, okay? Then any linear combination A of psi plus B of phi also belongs to the same vector space. The same is true for the Hilbert space. If we have two functions, psi and phi belongs to the Hilbert space, then any linear combination A of psi plus B of phi also belongs to the same Hilbert space. This was the first property. They are the same in both cases. The second property was distributivity with respect to addition. In case of vector space, we say that we have a scalar and we multiply it with two vectors psi and phi. The result will be A of psi plus B of phi. Or if we have two scalar, we add them first and multiply it with a vector. The result will be the same if we multiply each scalar individually with the vector. The same is true for the Hilbert space. If we have a scalar which we multiply with two functions such that first we add the two functions and then multiply the scalar, the result will be the same if we multiply the scalar individually with each function and then add the result. If we have two scalar, add the scalar first and multiply it with the function, the result will be the same if we multiply the scalar with the function individually and then add the function, add the result. This was another property, and we have few more properties which I don't want to mention here. You can see your previous lecture. Okay, now let's come to the next property of Hilbert space, which is property number 2. It tells us that the Hilbert space has a defined scalar product that is strictly positive. That is strictly positive. This is another property of Hilbert space. What it means, we will explain it in a detailed way here. If we have two functions, okay, that belongs to the Hilbert space. Suppose psi or phi are two functions that belongs to the Hilbert space. Then their scalar product, the scalar product of these two functions or these two elements of Hilbert space is a complex number. We multiply this, we represent the scalar product by this notation, psi or phi. This is the scalar product of two functions of the Hilbert space. If we get the scalar product, it will give us the complex number. We will discuss it in a detailed way below. Since the scalar product is a complex number, it means that psi or phi is not equal to, in general is not equal to phi over psi. Why? Because the scalar product psi over phi can be represented as psi steric. It's a complex conjugate sign, okay? Taking the complex conjugate of the first function and then multiply it with the second function. While phi over psi is equal to taking the complex conjugate of the first function and then multiply it with the second. So these two are not equal, okay? Because if we take the complex conjugate of the first, multiply it with the second phi. If we take the complex conjugate of phi and multiply with the psi, then obviously the result will be different. This is one of the property. The second property is the scalar product of psi with phi are equivalent like this. Psi over phi. The scalar product of psi with phi is equal to the scalar product of phi with psi only if we take the complex conjugate of this whole scalar product. We will prove it now. As we know that the scalar product taking left hand side, okay, which is psi phi, and this is equal to psi steric phi. Now taking the right hand side, which is phi psi steric. Steric means complex conjugate, okay? For example, if we have a complex number a plus iota b, suppose z is a complex number, then z steric is equal to a minus iota b. So this is the complex conjugate. Complex conjugate means we have to change the sign of imaginary part. So this is equal to, first I will represent it like this: steric phi psi. This is the scalar product. So we have the complex conjugate. If we open it, it will give us phi steric psi. And we know that if we have two number or two functions such as a or b complex number, okay, and then complex conjugate is equal to b steric, b complex conjugate, a steric, okay. So it comes from this property. Apply this property here, so it comes here to be psi steric phi steric whole steric, and we know that a steric whole steric is equal to a steric. For example, z is a complex number a plus iota b, then z steric is equal to a minus iota b. If we take again the complex conjugate, we get a plus iota b. So z steric whole steric is equal to z. So from this I will get psi steric phi. Right hand side is equal to this. If we compare the two equation 1 and 2, we see that left hand side is equal to right hand side, which means that psi over phi is equal to phi over psi with complex conjugate. In the next video, we will discuss other properties of Hilbert space.